Take a piece of tin, hold it in your hand. It feels ordinary. It feels cold, heavy, slightly dull. You probably associate it with old cans, cheap alloys, or maybe solder. For most of human history, tin has been one of the most unremarkable metals on Earth. Useful, yes, but not exactly the stuff of scientific revolutions. Now imagine being told that a team of scientists just squeezed that same tin down to a thickness of just a few atoms and discovered that it no longer behaves like tin at all. It becomes something else entirely, something that does not follow the rules of normal matter, something that opens a door into a quantum world that physicists have been trying to reach for decades, and that could rewrite the foundation of electronics, computing, and energy technology as we know it. That is not a hypothetical. That is exactly what happened in March 2025, and the world mostly missed it. Like and subscribe, because what scientists just found inside common metals is going to change everything you thought you understood about matter. To understand why this discovery is so profound, you first need to understand a fundamental truth about quantum physics that most people never learn. Quantum behavior, the strange, counterintuitive world where particles exist in multiple states at once, where electrons teleport through barriers, where matter acts like it is aware of being observed, was supposed to be confined to the incredibly small, to individual atoms, to single electrons, to systems so tiny they could never be seen with the naked eye. The classical world around us, the table, the chair, the metal in your pocket, was supposed to be comfortably separate from all of that weirdness. Classical physics for big things, quantum physics for tiny things. That was the deal. That was the assumption physicists made for most of the 20th century. But here is what they started discovering over the last few decades. That assumption is wrong. In certain materials, under certain conditions, quantum behavior does not stay confined to the atomic scale. It bleeds upward. It scales into the macroscopic. Entire sheets of electrons in a material can begin to act as a single quantum entity, correlated and entangled in ways that classical physics has no language to describe. And when that happens, the material stops obeying the rules you learned in school. It starts doing things that look impossible. Conducting electricity without resistance, switching direction based on the geometry of its lattice rather than any applied voltage, producing quantum effects that can be measured, controlled, and potentially used in technologies that make modern electronics look like stone tools. Like and subscribe, because what scientists pulled off with common metals in 2025 is exactly this kind of leap. Here's what they did. Researchers from the Institute of Physics at the Chinese Academy of Sciences, led by Professor Zhang Guangyu, developed a technique they called van der Waals squeezing. The concept sounds simple, but executing it was a decade-long engineering challenge that repeatedly hit walls that seemed physically impossible to cross. Metals, unlike materials such as graphene or molybdenum disulfide, do not have a natural layered structure that makes them easy to peel into thin sheets. In a material like graphene, the layers are held together by weak forces called van der Waals interactions, meaning you can literally use tape to peel off a single atomic layer. That is how graphene was first isolated. Metals are completely different. Metal atoms bond in all three dimensions with roughly equal strength. They are, in the famous analogy offered by the researchers themselves, like tightly compressed grains in a biscuit, bound together in every direction with no natural breaking point. Getting a metal down to atomic thickness was thought to be essentially thermodynamically impossible. The crystal structure would not allow it. Physics itself seemed to forbid it. Zhang Guangyu's team found a way around physics. They took pure metals, bismuth, tin, lead, indium, and gallium, and melted them into liquid droplets. Then they squeezed those liquid droplets between two rigid layers of molybdenum disulfide, which serves as an atomically flat anvil, applying pressure of 200 megapascals. As the pressure held and the temperature dropped, the metal solidified not into its usual three-dimensional bulk structure, but into an atomically thin, two-dimensional sheet, completely encapsulated between the two molybdenum disulfide layers, protected from oxidation, stable at room temperature for at least a year. The published paper in Nature on March 12, 2025, named 5 metals they had successfully produced this way. Bismuth at around 6.3 angstroms thick, tin at around 5.8 angstroms, lead at around 7.5 angstroms, indium at around 8.4 angstroms, and gallium at around 9.2 angstroms. To put those numbers into perspective, a single angstrom is 1/10 billionth of a meter. These metal sheets were 2 to 3 atoms thick. They were the thinnest metal materials ever created in human history. Like and subscribe, because what happened to those metals when they reached that thickness will genuinely stop you in your tracks. When tin was squeezed down to its two-dimensional form, it did not just become thinner tin. Its entire electronic behavior changed. In bulk, tin conducts electricity in the way metals normally do. with electrons moving through a three-dimensional structure according to well-understood classical rules. In its two-dimensional form, squeezed to less than 6 angstroms, something entirely different happens. The electron motion, which had been spread across 3 dimensions, is now confined to a plane. And in that confinement, the rules change completely. As co-corresponding author and researcher, Du Lojun described it in a press release, when metals are compressed to atomic thickness, electron motion shifts from 3-dimensional to 2-dimensional. He called it like turning an ocean into a water film, where exotic quantum fluctuations inevitably emerge. That phrase is worth sitting with for a moment. Exotic quantum fluctuations. Not theoretical, not predicted on paper. Actually measured in a real material made from a common metal that anyone reading this has almost certainly handled. Like and subscribe, because the word exotic does not even begin to cover what these fluctuations can do. The researchers measured several remarkable properties in their 2-dimensional bismuth sample. First, the electrical conductivity was significantly enhanced compared to bulk bismuth. In its normal 3-dimensional form, bismuth is actually a poor conductor, unusual for a metal. In its atomically thin 2-dimensional form, the conductivity jumped sharply, but that was the least surprising thing they found. More striking was a property called large nonlinear Hall conductivity. In a normal conductor, when you apply a magnetic field perpendicular to the current flow, the electrons are deflected sideways and you get a small sideways voltage called the Hall effect. This is well understood and has been used for sensors and measurements for over a century. But the nonlinear Hall effect is different. It generates a sideways voltage even without any magnetic field at all, purely from the geometry and quantum properties of the material's electronic structure. In 2-dimensional bismuth, this effect was enormous by the standards of materials that display it. That is a direct signature of quantum geometry, of the electrons in the material responding to the curvature of their quantum mechanical wave function in ways that produce measurable, usable electrical behavior. Like and subscribe, because this is where common metals stop being common and start being the future of technology. They also observed entirely new phonon modes in the 2-dimensional bismuth. Phonons are the quantized vibrations of a crystal lattice, the quantum mechanical version of sound waves moving through a solid. In bulk bismuth, the phonon spectrum is well known and well characterized, but in the 2-dimensional form, new vibrational modes appeared that have no counterpart in the bulk material. This means the material is not just thinner bulk bismuth. It is a fundamentally different quantum object, with a different set of allowed quantum states, a different set of possible vibrations, and a different relationship between its electrons and its crystal structure. The researchers were clear in their Nature paper that these properties represent only the beginning. They wrote explicitly that the 5 2-dimensional metals they had demonstrated were just the tip of the iceberg for their method. They identified what they called a knowledge gap in the emerging electrical, optical, and magnetic properties of 2-dimensional metals compared to their bulk counterparts, meaning that even they do not yet fully understand everything these materials are capable of. To understand why this matters so deeply, it helps to understand what happened when graphene was discovered. Graphene is a single layer of carbon atoms arranged in a hexagonal lattice. It was first isolated in 2004 by André Geim and Konstantin Novoslov at the University of Manchester, using the now famous Scotch tape method. Within 6 years, they had won the Nobel Prize in physics. Graphene turned out to have extraordinary properties. It conducts electricity better than copper at room temperature. It is harder than diamond. It is nearly transparent, and its electrons behave like massless particles moving at a fraction of the speed of light. The discovery of graphene opened an entire new field of physics and materials, science called 2-dimensional materials, and it triggered a global race to find other materials that could be peeled down to atomic layers and might exhibit similarly extraordinary properties. But graphene is one specific material. It is a single layer of carbon. For nearly 2 decades, the family of easily accessible 2-dimensional materials was largely limited to compounds that already have a natural layered structure. Materials like molybdenum disulfide, hexagonal boron nitride, and related compounds. Metals, the most technologically important class of materials in human civilization, were locked out of this world. They could not be made 2-dimensional. Until now. Like and subscribe, because the door that just opened is not just for bismuth and tin. It potentially opens every metal on the periodic table to quantum engineering. The Physics World Journal, one of the most respected publications in the field, named the 2-dimensional metal breakthrough its Physics World Breakthrough of the Year for 2025. That distinction does not come lightly. It is awarded annually to a single result that the editors judge to have made the most significant contribution to physics, representing the most important advance of the year across all of physics. And they gave it to a technique for squeezing common metals into atomic sheets. That alone should tell you how significant this is. But the broader physics community has also reacted with unusual unanimity. A review paper, published in Nature Reviews Physics in April 2026, confirmed that the van der Waals squeezing method can produce multiple two-dimensional metals at angstrom scale thickness, while keeping them environmentally stable for at least 1 year. Environmental stability is critical because many novel quantum materials are exquisitely sensitive and degrade within hours or days of being exposed to air. The fact that these two-dimensional metals remain stable for a year in encapsulated form means they are candidates for real devices, not just laboratory curiosities. Now, let us connect this to the other revolution happening simultaneously in quantum metals, because the timing of this discovery is not coincidental. It is part of a much larger scientific awakening about the quantum world hidden inside ordinary materials. Physicists at Rice University published a landmark paper in Nature Communications in March 2025 that cracked a mystery which had baffled condensed matter physics for nearly 4 decades. The mystery involved what scientists call strange metals. Unlike familiar metals such as copper, predictable, well-understood ways governed by the behavior of individual electrons, strange metals behave in ways that defy every standard model of how metals are supposed to work. Their electrical resistance changes linearly with temperature in a way that no theory of classical electron scattering can explain. Their electrons seem to lose their individual identities entirely. The standard picture of electrons as particle-like objects moving through a lattice breaks down completely. For decades, physicists called this the strange metal problem, and it sat at the heart of some of the deepest unsolved questions in physics, including why certain copper-based materials can superconduct at temperatures far higher than any standard theory predicts. The Rice University team, led by Chimiao Si, decided to attack the strange metal problem using a concept borrowed from quantum information science called quantum Fisher information. This mathematical tool measures how entangled the quantum states of a system are, how deeply correlated the particles are in a quantum mechanical way. When they applied this measurement technique to strange metals, they found something astonishing. At a specific tipping point called the quantum critical point, where a strange metal transitions between 2 different quantum phases, the electrons become dramatically more entangled than at any other condition. The entanglement does not gradually increase. It peaks sharply, explosively, right at that critical point. And it is that explosion of quantum entanglement that produces all the anomalous behavior. The strange resistance, the lost quasi-particles, the violation of standard metallic rules. The mystery of strange metals was not that they were doing something exotic for no reason. It was that they were doing something quantum, something deeply entangled, in a way that classical physics was simply not equipped to see. Like and subscribe, because scientists just confirmed that the weirdest thing in condensed matter physics is driven by the same quantum entanglement that makes quantum computers possible. Why does any of this matter for the future? Because these 2 streams of discovery, the creation of two-dimensional metals and the revelation of quantum entanglement inside strange metals, are pointing toward the same horizon. That horizon is a new generation of electronic and quantum devices built not from the carefully engineered exotic materials of today, but from thin sheets of common metals whose quantum properties are unlocked by geometry and confinement rather than rare earth elements or extreme fabrication processes. Consider what the two-dimensional metals could offer to electronics. Modern transistors, the switches that make every calculation in every computer on Earth, are built from silicon and are approaching their physical size limits. When silicon transistors get below about 5 nanometers in size, quantum tunneling effects make them unreliable. Engineers have been searching for materials that can take over where silicon leaves off. Two-dimensional metals offer something silicon cannot. They are already at the atomic limit. Their electron behavior is already quantum. And as the researchers demonstrated with bismuth, some of them show exceptional field effect behavior, meaning their electrical conductivity can be switched and tuned by applying an electric field, exactly the property needed for a transistor. A follow-up study published in October 2025 from the Singapore University of Technology and Design explored precisely this possibility with two-dimensional bismuth. When pressure transforms bismuth from its natural semiconducting atomic layer form into the metallic form produced by van der Waals squeezing, the material becomes switchable. By sandwiching it between 2 layers of molybdenum disulfide and applying an electric field, the researchers demonstrated something they called layer-selective ohmic contact, where current could be directed to flow through specific layers of the structure on demand. This is essentially a demonstration of a new type of transistor built from atomically thin metal, controlled by an electric field, operating at the quantum limit of material thickness. The implications for ultra-miniaturized electronics are enormous. Like and subscribe, because the transistors of the next generation might be built from the tip of a tin can. The relevance to superconductivity and quantum computing is equally striking. Superconductors are materials that conduct electricity with zero resistance when cooled below a critical temperature. They are extraordinarily useful for energy transmission, powerful magnets, and most critically, for building qubits, the fundamental processing units of quantum computers. The problem with known superconductors is that most of them only work at temperatures close to absolute zero, requiring expensive and temperature superconductors, which work at warmer but still very cold temperatures, exist in materials that include copper oxide compounds called cuprates. Strikingly, the cuprates are among the primary examples of strange metals. Understanding why strange metals behave the way they do is directly connected to understanding why certain materials become high temperature, superconductors, and whether we can design new ones. The Rice University discovery about quantum entanglement in strange metals brings that understanding significantly closer. If the mechanism of strange metal behavior is quantum entanglement at a critical point, then controlling and engineering that entanglement through techniques like van der Waals squeezing that reshape the quantum geometry of a metal becomes a realistic path toward designing room temperature superconductors from scratch. Like and subscribe, because room temperature superconductors would eliminate power loss and electricity transmission globally, are saving trillions of dollars annually and transforming how every device on Earth uses energy. The connection to quantum computing does not stop at superconductors. The two-dimensional metals created through van der Waals squeezing display properties called nonlinear Hall effects and new phonon modes that are direct signatures of topological quantum states. Topology in physics refers to properties of a material's electronic structure that are preserved even when the material is distorted, stretched, or compressed. Properties that are robust against noise and disorder in a way that conventional quantum states are not. Topological quantum states are exactly what scientists need to build. Topological qubits, a form of qubit that stores quantum information in a non-local, inherently protected way that resists the decoherence problem that currently limits quantum computers. Microsoft has been pursuing topological qubits for years using rare and difficult to fabricate exotic materials. The revelation that atomically thin common metals exhibit signatures of topological behavior means that the building blocks for topological quantum computing might be accessible through a straightforward manufacturing process applied to materials you can find in a hardware store. That is a paradigm shift. Like and subscribe, because scientists just discovered that the raw material for fault-tolerant quantum computers might have been sitting in your plumbing for a century. The van der Waals squeezing method is also significant because of its versatility. The researchers were explicit that their 5 initial metals represent only the beginning. Their method works on any metal that can be melted and squeezed and applies to metal alloys and non-van der Waals compounds as well. The ability to tune the thickness of the two-dimensional metal layer with atomic precision, choosing monolayer, bilayer, or trilayer, gives researchers extraordinarily fine-grained control over the quantum properties of the resulting material. Different thicknesses produce different electronic band structures. Different band structures produce different quantum phases. The entire landscape of quantum phases in two-dimensional metals is now, suddenly, explorable. There is also a photonic dimension to this story generating significant excitement. In two-dimensional metals, quantum confinement changes how electrons respond to light in ways not yet fully characterized. The researchers noted explicitly that the optical properties of these materials represent an open scientific question. What is already known is that enhanced electrical conductivity and altered phonon structure will produce optical behaviors unlike anything seen before, highly relevant as photonic. Computing, using light instead of electrons to carry information, gains rapid traction globally. And what makes the timing of all these discoveries particularly striking is that they are converging. The two-dimensional metal breakthrough, the strange metal entanglement discovery, the growing understanding of topological quantum states. In thin-film materials, the demonstration of layer-selective switching in atomic-scale metal transistors, these are threads of the same fabric. They are telling a consistent story about the hidden quantum world inside materials that humanity has worked with for thousands of years without understanding what was lurking below the classical surface. For most of human history, a metal was a metal. Dense, opaque, useful for building and conducting. The quantum world inside it was invisible and irrelevant to everything we did with it. In 2025, that invisibility ended. The practical road from these discoveries to commercial technologies will not be short. Scaling the van der Waals squeezing technique to industrial production is a genuine engineering challenge, and understanding the full range of quantum properties in two-dimensional metals will take years of careful measurement and theory. But the trajectory of the science is clear, and it is pointing somewhere extraordinary. A future where computers are built from atomically thin metal films that exploit quantum geometry. A future where power grids transmit electricity without any loss. enabled by superconductors designed through quantum engineering of metals considered mundane today. A future where quantum computers use topological qubits made from materials that currently solder circuit boards and package food. The hidden quantum world inside a common metal did not just change everything, it changed the question. For decades, physicists asked what exotic, rare, painstakingly fabricated materials could unlock quantum behavior in useful forms. The answer, it turns out, may have been sitting in the periodic table the entire time. In bismuth, in tin, in gallium, and lead, and indium, in the metals of civilization. What changed in 2025 is not that these metals became quantum, they always were. What changed is that we finally found a way to listen to them, like and subscribe, because the next great technological era will be built. From materials that have been in your kitchen, your plumbing, and your electronics for generations, just finally understood for the first time.